Okay, so yesterday we started laying a foundation on some of the things we are going to use in order to carry out a bit of research on gravitational fields. Yesterday we were able to make some comparisons between Einstein's theory of gravitation and the dynamical theory or Newton's theory of gravitation. And we are also able to agree that electromagnetism and gravity are two distinct forces. And we also agreed that we can use tensors in a general relativity or a gravitational field. And we agreed that a scalar quantity is a tensor of rank 0. We also agreed that a vector is a tensor of rank 1. And then we agreed that there are other tensors of rank 2, there are tensors of rank 3, and tensors of rank 4. And we said we will not go beyond 4. Okay? And we also agreed that the basic building block in a gravitational field is what we call a metric tensor. We agreed that it's a metric tensor. Now, once you have the metric tensor, you can be able to do a number of things in a gravitational field. And yesterday, I introduced two equations that are used in general relativity. I introduced the field equation, and I equally introduced the field equation and the okay. This button seems to have a problem. The other one going. Okay. So we introduced the geodesic equation of motion. Okay, where we agreed yesterday that this is the, what did we say this is? The coefficient of affine connection. Okay, so we had this equation, and we equally had the second equation. Okay, we had the field equation, and in the field equation we said the G is the Einstein tensor and the T is the stress tensor. Okay, and the Einstein tensor is defined in this way, and the stress tensor is defined in this way. Okay, in the morning we saw a lot of density and pressure. Okay, so the right hand side, what we call the stress tensor, has contribution from the density and the pressure. Okay, while the left hand side comes directly from the metric tensor. Okay, so yesterday I also said that this is our superhighway. Okay, that will start from here, from the covariant metric tensor to the contravariant metric tensor to the affine connections to the Riemann-Christoffel tensors to the Ricci tensor to the curvature scalar and to the Einstein tensor. Okay, once you move through that to get the field equations. Okay, so I have chosen one of the simplest solutions to the field equations we just saw. Okay, so one of the solutions to this field equation is what we call Schwarzschild solution. Schwarzschild solution. So we are going to take much time on this Schwarzschild solution and do a number of things. Then from there, you'll be able to get an experience on how to work on other solutions. Okay? And actually, Schwarzschild solution is a solution to Einstein's field equations outside a spherically symmetric mass placed in empty space. Okay? You have a spherically symmetric mass in empty space. So we're assuming that outside the mass there is no gravity. That the gravity is only contributed by the spherical body. So the spherical body is placed maybe somewhere in vacuum. Somewhere where there is no contributing field near it. Okay? So, in essence, this is a summary of Schwarzschild's solution. And this is the metric tensor in Schwarzschild's field. So that metric tensor has only 4 components. Okay? Remember, we agreed yesterday that there are supposed to be 16 components. So what we are saying here is that the other 12 are 0. The other 12 components are 0. Okay? So M is actually the mass of that spherical body. Okay? And R is the radial distance. Okay? So those are the 2 parameters we have there. So this solution is expressed in spherical polar coordinates. Okay? It's expressed in spherical polar coordinates. And I've set down here that other solutions exist. There are many other solutions. Okay? There is the Neumann metric, there is the Kerr metric, and many others. Well, we are going to use this one as our example. Okay? Once we go through Schwarzschild's solution, and I give you any metric, you can then be able to get some of the parameters we'll be interested in. Okay? That is our... Okay. So, what are the astrophysical phenomena we are going to study using Schwarzschild's metric? The first one is what we call Schwarzschild's singularity. What is a singularity? What is a singularity? On mathematical methods, you know of a singular point. Okay? And actually, there are 2 types of singular points. Irregular and a regular point. So what is a singularity? Who can remind us? A point where a function is not defined. Okay? A point where a function is not defined is a singularity to that function. Okay? So we can have singular points. We can have singular points. So we are going to look at Schwarzschild's singularity. We stated Schwarzschild's solution as G00 equal to 1 minus 2gm over c squared r. Okay? And then we had G11 as 1 minus 2gm over c squared r to the power minus 1 over G22. I think there's a minus here. It's minus r squared, and our G33 is minus r squared sine squared theta. Am I correct? Am I correct? Okay, that's what we said. Okay, so we can write this as a line element. As a line element, ds squared is equal to, okay, c squared G00, the tau squared, minus G11, the r squared, minus G22, the theta squared, minus G33, the phi squared. Okay? Remember, the other terms are 0, so we end up only with these 4. We have only these 4 terms. So if we substitute our values for our components of the metric tensor, we are going to have c squared into 1 minus 2gm over c squared r, the tau squared, minus, okay, 1 minus 2gm over c squared r to the power minus 1 the r squared, minus r squared the theta squared, minus r squared sine squared theta the phi squared. Okay? So actually this is, yeah, it's okay. I'll leave it like that. So that is our line element. So if you look at this line element, you will discover that there's a possibility of a singularity. There's a possibility of a singularity. If you look at the second term, this term is at the denominator. Are we together? Because of the minus 1. So I can write this as the r squared over all of that. Are we together? So what if what is at the denominator becomes 0? We have dr over 0, which is infinity. Are we together? We have dr over something that is 0. So for us to get that Schwarzschild singularity, we need to equate this to 0. Okay? And if we do that, we'll realize that our r will be what? 2gm over c squared. And we'll give that r a subscript of s, showing that it's a special r. Okay? It's a special r that makes this metric, this line element to be undefined. So once r takes this value, this line element will be undefined. Because if you substitute that r here, you have 1 minus 1. You substitute it here. Okay? You have 1 minus 1 and it will be 0. So we're calling it, we call this the Schwarzschild radius. Okay? We call it the Schwarzschild radius. And if you want to calculate this for the Earth, what is the mass of the Earth? What is G? 6.67 times 10 to the power. Okay. What are the units? Are you sure? Newton? Okay. And then what is the mass of the Earth? What's the mass of the Sun? This guy, you have to tell us. You have to tell us. You have to tell us the mass of the Sun and the mass of the Earth. Or I'll call Professor Bachuku and tell him that you don't know the mass of the Sun and the mass of the...
Let me give you the mass of the Earth.
Yes, Prof.
5.972 times 10 raised to the power of 24 kilograms.
Okay.
Mass of the Sun. Mass of the Sun.
Yes, sir.
1.98 times 10 raised to the power of 30 kilograms. But you can also convert a bit of mass to solar logics.
Yes. Yes. Okay. So we have that. What about C? Okay, 3 times
10 raised to the power of 8 meters per second.
meters per second. So if you substitute that for the Earth, you will get something around 0.89 centimeters. Okay, you get something around 0.89 centimeters. What is the radius of the Earth? I'm looking at you. Okay, 6,400 kilometers. That's the radius of the Earth. So you see, we are getting a distance smaller than the radius of the Earth. Okay, so you are seeing that Schwarzschild's radius for the Earth lies within the Earth. It's not outside, it's within the Earth. And our metric is an exterior metric. The metric we are using is a metric exterior to the body. But our Schwarzschild's radius is lying within the body. Okay? So what it simply says is that within the body, the metric you need to use is the interior metric. But we have an exterior metric. So an exterior metric cannot be applicable in the interior. So if you want, but there are some objects or some astronomical bodies whose Schwarzschild radius is exterior to the body. Okay? And such bodies, we call them black holes. Okay? Bodies that have their Schwarzschild radius exterior to the body. So if you want the Earth to become a black hole, you need to reduce the radius of the Earth from 6,400 kilometers to 0.89 centimeter. In that case, I don't know how many of us will be left. If we reduce the radius of the Earth from 6,400 kilometers to less than a centimeter. Less than a centimeter. Will my finger even fit in? Will my finger fit into the... It will not fit in. Okay? So we have that. So what do we know about black holes? You have been hearing about black holes. Okay, I think they even say there is one at the middle of our galaxy. Is it a point? Is a black hole a point? Uh-huh. Where?
Let me read something for you.
It's okay, sir.
A black hole is a region in the space-time where gravity, see, because we are looking at that in the relativity domain. So, gravity is so strong that nothing, including light and other electromagnetic waves, has enough energy to escape it. Anything that goes in
Will not come out. And anything that is in, it remains in. Okay? So that is a black hole. That is a black hole. Okay? So once you have a metric, you have a line element, you start looking at points of singularity. Because any point of a singularity will define a black hole. Okay? A black hole. It's okay. So, is there any question on that? We are through the first astronomical phenomena. The second one is what we call gravitational length contraction. Gravitational length contraction. Gravitational length contraction. Okay, in special relativity, you have also seen length contraction due to speed. Okay, when something is moving at a very high speed, there is also length contraction. Okay, but we want to look at the situation where the contraction is caused by the presence of a gravitational field. By the presence of a gravitational field. Okay? So, what is our line element in empty space where there is no gravity? Where there is no gravity, our line element looks like this. Squared minus, I think I have it somewhere, minus the r squared minus r squared, the theta squared minus r squared, sine squared theta, the phi squared. That's our line element in empty space where there is no gravity. So in that case, our G00 is 1, our G11 is minus 1, our G22 is minus r squared, our G33 is minus r squared sine squared theta. I hope you can deduce this from this. Look at it. We have c dt, we have dr, we have d theta, we have d phi. We also have c dt, dr, d theta, d phi. Okay? So actually this is 0, this is 1, this is 2, this is 3. Same this way. Okay? So what I expect to have here is c squared dt squared, which is my g 0, 0. Okay? What I have here is c dt dr, which is g 0, 1, which is 0 in our case. There's no term here that has dt dr. We look at this metric, there's nothing with dt dr, so it's 0. Can you see that? Okay, the next one will be c dt d theta, which is our g 0, 2. Again, it's also 0. And if you look at it, only the diagonal elements will survive. So you have the r squared here, you have the theta squared, and you have the phi squared. So only these ones will survive. The others will be 0, 0. The others will be 0, 0. So only the diagonal elements will survive. Okay, so this is our metric tensor in empty space where there is no gravity. That's our metric tensor in empty space. Okay, so let's assume that we have a point. Okay, let's consider two radial points. Okay, let's consider two radial points or 2 points where phi and theta are not changing. That's along a radial line. We are moving along a radial line, the angles don't change. Is that not? Theta remains theta, phi remains phi. When you are moving along a radial line. Okay? So if we are moving along a radial line, the theta will be equal to the phi will be equal to 0. Is that not true? Since the angle is not changing. So we have that. And if we consider only the space part, because remember we are talking of length, and length is a space parameter. Okay? So we'll consider only the length part of the metric. We will not consider the time part of the metric. We'll consider only the length part of the metric. So if we consider only the length part of the metric, then what we are saying is that our ds squared will be the same as dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. We are considering only the space part. Okay, we are considering only the space part. Our line element will look like that. So if we now have two radial points where d theta, d phi is 0, then we'll end up with this term dropping and this term dropping. Are we together? The last two terms will drop, and you end up with the s squared being the same as the r squared. Okay. Actually, we are working in what we call this minus is from the type of metric we are using. Okay? So it's just c squared, the t squared minus the s squared space. That's how the metric is defined. So the minus is appearing just because of this. Actually, the space part is positive. Are you getting the point? The space part is positive. But because we are dealing with, I think we call it a Minkowski's space. Okay? That is why we have this minus sign. So when I'm isolating the space part, the minus will not appear. Are you getting the point? The minus will not appear. So we now have this. So with this, we can now say the S is the same as the R. Okay? So what do we conclude from there? What we conclude from there is that the proper distance is equal to the radial distance, or the coordinate distance. Because dr is the coordinate distance, and s is the proper distance. So the proper distance is equivalent to the radial distance in empty space. In the absence of gravity, the proper distance is equal to the radial distance. What if we now bring in gravity? Okay, it's the same approach Prof was using in the morning. Take away gravity and see how it behaves. Okay? Bring in gravity and see how it behaves. So we are going to do the same. So we have seen that without gravity, the proper distance is the same as the radial distance. So let's now bring in gravity and see how it behaves. And we are going to bring in gravity using our Schwarzschild metric. Any questions so far? Any questions so far? Okay. So far, so good. The class is so quiet. I hope you are not seeing the rice and the chicken. Because it's possible you can be sitting and looking at me and you are only seeing rice and chicken. Okay. It's okay. So let's look at, in the presence of gravity, the s squared is c squared, the t squared minus 1 minus 2gm over c squared r. Okay, this one is supposed to come in here. It's supposed to come in there. So we have c squared into 1 minus 2gm over c squared r. Okay. The t squared minus 1 minus 2gm over c squared r. The r squared minus r squared. The theta squared minus r squared. Sine squared theta. The phi squared. Okay. Okay. Try to compare this and this. Can you see the difference? This is empty space. This is in a gravitational field. Okay, so you have that. So again, we'll isolate the space part. So isolate the space part it will be just 1 minus 2 gm over c squared r, the r squared plus r squared the theta squared plus r squared sine squared theta the phi squared. That's the space part. Okay? That's the space part. And then again, we are going to consider motion along a radial distance. So again, our d theta, d phi will be 0. So we'll end up with the s squared being equal to 1 minus 2 gm over c squared r to the power minus 1 dr squared. Look at what we had here. And look at what we are having here. So here we agreed that the proper distance is the same as the coordinate distance. But here we are seeing that that is not true. Okay? We are seeing that that is not true. And I want to claim that, okay? I want to claim that the s squared is greater than the r squared. That is my claim. Am I correct? Am I correct? Am I correct? Who is saying yes? Why? Okay. Who has another idea? My guy, you said yes. Okay, yeah, look at the eye. Yes. Okay. No, what? Yeah. So you see, for you to get the s squared, you need to add the r squared plus something. So it's showing that the s squared is greater than the r squared. Because the first term, as he says, produces the r squared. And then you have another term again and another term. Okay? So you need the r squared plus another term to give you the s squared. So the s squared is greater than the r squared. Are we together? So what is this saying? It's saying that actually there is some sort of contraction. The s is no longer equal to the r. But the r is now less than the s. And remember, the r is the coordinate distance. It's the coordinate distance. Actually, the s is the proper distance, which is measured, we always say is measured at infinity. It's measured in the absence of gravity. And the r is the distance that is measured in the presence of gravity. That's why this one is called proper, and this one is called coordinate. Okay? So this is the proper time measured at infinity, or measured in the absence of gravity, and this is the coordinate time. So you are seeing that the coordinate time is contracted. there's some sort of contraction. And that is what we are calling gravitational length contraction. Okay? That's what we are calling gravitational length contraction. Okay? And actually, in the theory of gravity, it's not only the length that is contracted, even space itself is also contracted. Okay, even space itself is also contracted. If you remember yesterday, I told you that gravity curves space. Gravity curves space. So if you have something of this length and you curve it, the length will not be the same. Is that not? If something is like this and I want to measure the length across it, it will not be the same. Okay? So if the presence of gravity curves space, it also contracts length. So if something is, yes?
So, I think that should now explain why they say the principle of this time, the shortest possible distance,
That is it. That is it. Okay, so you move along a geodesic. Move along a geodesic. Okay? So we have that. So space is curved. Space is curved. So that is, so in a situation where an object is moving at a very high speed and is inside a gravitational field, okay, there is length contraction due to speed. We have length contraction due to speed, and we have length contraction due to the presence of a mass. So if you have an object that is moving at a very high speed, in the presence of gravity, then you need to marry the two. Okay, you marry the two to give you your proper length contraction. Are we together? Are we together? Any question? Any question? Yes, sir. Okay. Does it have magnetic field effects? Okay. That is it. That is it. So, for Schwarzschild metric, magnetism is not considered. It's not considered. Okay? It's not considered. The metric we are going to see later, it does not also consider magnetism. It does not also consider magnetism, but it is better than this other one, in the sense that the interior of the star is more populated compared to Schwarzschild metric. Actually, in Schwarzschild metric, the spherical body is assumed to be gaseous. Just be a normal gaseous sphere. Okay? Assumed to be a normal gaseous sphere. So what if it's not a normal gaseous sphere? What if it is more populated? How would the gravity be affected? Okay, that's why there are so many metric tensors trying to study different situations and so on. Okay? So let's look at time dilation. Let's look at time dilation. Let's look at time dilation. Okay. I can write this as Okay, I can write this as c squared d tau squared, where my tau is the proper time. Remember, this is the proper distance. Okay, and remember, this is also a distance. This is also a distance. Okay, speed by time is also a distance. So I can write my left hand side as this. Are we together? Okay. So what if I consider a clock that is at rest in empty space? A clock that is at rest in empty space. In that case, the clock is not moving. So my dr will be 0, my d theta will be 0, my d phi will be 0. The clock is at rest. Okay? If I have a clock at rest, my dr will be 0, d theta will be 0, d phi will be 0. So my line element will reduce to c squared d tau squared equal to c squared dt squared. From there, my d tau will be the same as dt. Okay, so my proper time interval is the same as my coordinate time interval in the absence of a gravitational field. Okay. Okay, they used to include the Lorentz factor in special relativity. That is in special relativity. When you are, remember when I was talking of length contraction, I said there's also special relativity length contraction. The same as there is also time dilation in special relativity. Okay? So you have that. Are we together? Any questions so far? So far, so good. So what if we now introduce a gravitational field? What if we now introduce a gravitational field? And again, we are considering a clock at rest. Okay? Again, we are considering a clock at rest. So we are going to end up with c squared d tau squared equal to, so only the first term here will survive. All the other ones will go away. So I will have c squared 1 minus 2 gm over c squared r dt squared. Only the first term is going to survive. So from there, I will claim that my dt is the same as 1 minus 2 gm over c squared r to the power minus 1 d2. Am I correct? Okay, and then from there, using the same argument, we are going to say that dt is greater than d2. Is dt greater than d2? Is it greater than d2? Have you seen it? This is why you are drinking water. Okay. Yeah, because once we expand this, we have 1 plus. Okay? Once we expand this, we are going to have 1 plus 2 gm on c squared r plus another 10. All of that, the 2. Okay? So you discover that the t is greater than the 2. So the coordinate time is more than the proper time. So gravitation has dilated the time. Okay? In the other case, gravitation contracted the length. But in this case, we are seeing gravitation making the clock to run slower. Okay? Gravitation is making the clock to run slower. Okay? Not to tick faster. Okay, so in a relativistic case, in a special relativistic case, you now add this other expression for gravitational length dilation together with the special relativistic case. So it now gives you a true representation of what is happening. Any questions so far? Any questions so far? Okay, let's look at the last phenomenon for today. For today, we'll continue from there tomorrow. Gravitational spectral shift. Gravitational spectral shift. Okay. When we talk of spectral shift, what comes to your mind? When we talk of spectral shift, what comes to your mind? When you talk of a spectrum, what comes to your mind? Huh? Waves will come to your mind, light will come to your mind, and so on and so forth. Okay? So we are going to have a spherically symmetric mass, okay, situated in empty space. Okay? And we have maybe an emitter here, something here that's emitting a pulse of light. And then there's a receiver here. Okay? There's an emitter and there's a receiver. So it's emitting a pulse of light from here, and the pulse of light is received at the other end. Okay? We are going to see that the relative positions of the emitter and the receiver matter. Okay? Which of them is closer to the massive body? Is it the emitter or the receiver? Okay, if the light is emitted at a further distance to the okay, if the emitter is further away than the receiver from the massive body, there's a different type of shift. And when we have maybe the emitter here and the receiver here, there's also a different type of shift. So we're going to see there are two types of shift: a red shift and a blue shift. Okay? We're going to have a red shift and a blue shift. Okay? We have a red shift and a blue shift. If I'm going this way, what increases? What increases? Okay? And if I'm going this way? I hope we all know this. Mauga? Okay. So, a red shift is that the wavelength of the light will move towards red. A blue shift is that it will move towards blue. So the wavelength of the light will increase. In this case, in a red shift, the wavelength of the light will reduce. So if the wavelength is reducing, then it's moving towards red. If the wavelength is increasing, it's moving towards blue. Okay? So we're going to have that. Okay? So in the first case, let's consider an emitter that is further away. Let's consider this case. And a receiver. Okay? And then before we go into that, we need to agree that light moves along what we call a null geodesic. Light moves along a null geodesic. And what do we mean by a null geodesic? What we simply mean is that the S squared equal to C squared, the tau squared equal to 0. Okay? We are going to treat the movement of light different from the movement of test particles. Okay? The movement of light, we are going to treat it different from the movement of particles. So from there, we see that the tau is 0. So actually, this is the equation of motion of light in a gravitational field. Okay? This. So light moves along a null geodesic. Okay? So if we have a receiver here, then the coordinates of the receiver will be TR, R dot, theta dot, and so on. But remember, we are moving along a radial line. So theta and phi will disappear. Okay? So you have these general coordinates. Are we together? So what is our line element? Our line element is C squared d tau squared equal to 1 minus 2gm. Or C squared R dt squared equal to minus 1 minus 2gm over C squared R, the R squared minus R squared, the theta squared minus R squared sine squared, theta, the phi squared. So if we all agree that light moves along a null geodesic, then the right hand side will be 0. The left hand, is it the left hand side or the right hand side? Okay, it's left to you, but to me is. Okay, I'm supposed to face it. Okay, so it's the left hand side. Okay. So I should talk and face the board and not face you. Because if I'm facing you, then my own right hand side is your left hand side. So this will be 0. And if this is 0, then I want to minimize my writing. So if this is 0, then what I'm saying is that this one is equal to this one. This one is equal to this one. Do we agree? Do we agree? I want us to agree. Are we together? Only one person has said yes. Are you tired? You better not be tired. You better not be tired. Okay. I want to replace my GM by K. Okay. I want to replace my GM by K. Are we together? And secondly, I want to introduce a parameter U that I can use to monitor the motion of the body. A parameter U that I can use to monitor the motion of the body. If I have that parameter U, I can decide to write this equation as c squared 1 minus 2k over c squared r. Okay. Is this correct? So I've introduced a parameter U all through. Are we together? I've introduced a parameter U at the denominator throughout. Okay. And I want to make the T du the subject of this formula. So what will my dt du look like? My dt du will be the same as 1 over c squared into 1 minus 2k over c squared r to the power minus 1 over 2 ds. Maybe I should use a star on this s so that we differentiate it from the normal s that we had earlier. Okay? So what has happened is that I have decided to call all of this on the right hand side. I've decided to call it ds squared. Okay? Then automatically I've divided both sides by c squared, and this one I'm going to the other side will take a minus. Okay? And then when you take the square root, the square on this one will disappear and a half will be introduced here. The one on C2 should. Where? Okay, the one on C2 should also go. Yes. That on C2 should also go. You are talking of a minus. Okay, the minus has suddenly disappeared. Okay. So we are going to have this. That looks beautiful. Looks beautiful. Okay. So my dt will be 1 over c into 1 minus 2k over c squared r to the power minus a half ds star, all of that du. Are we together? If I take this integral, I take this other integral, so this will move from t emitter to t receiver. Okay? Because our signal is moving from emitter to receiver. So the emitter is the initial point and the receiver is the final point. Okay, I can also introduce a U emitter and a U receiver. Okay, remember C is a constant, so it can come out of the integral sign. It can come out of the integral sign. Okay. So we have that. There's one interesting argument we want to make at this point. I hope the thing is having a human face. One of my students said that what I'm teaching them is having a masquerade face. It looks like a masquerade. It doesn't look like a human being. But I hope this has a human face. It should have a human face. Okay, it should not look like a masquerade. Okay. So, what if I have two signals? I emit one, and then after some time, I emit another one. You get the point? I emit one signal, it goes from my emitter to receiver. And then after some time, I emit another one. It goes from my emitter to my receiver. And the two signals have the same properties. Same wavelength, same frequency. What I want to claim is that this interval will be the same for the two signals. So if I have my signal 1, then my TR1 minus TE1 will be the same as my TR2 minus TE2 for the second signal. Okay? The time interval that it takes for the signal to move from emitter to receiver will be the same for the two, because they have the same properties. Okay? They are moving from the same one point to the next point, and they have the same properties. So the time interval it will take from receiver, whether from emitter to receiver, will be the same for the two signals. Is that not true? Yes. The points are not moving. The points are not moving. We just have an emitter here and a receiver here. The points are fixed in space. Okay? So the time it will take for the first signal to move from here, the time difference between the two signals should be the same. If the two signals have the same properties. Okay? So looking at this, I can let me put it this way. If I take this to this other side, I will have TE2 minus TE1 should be equal to TR2 minus TR1. So what again are we seeing there? That the interval between two emissions is the same as the interval between two receptions. Okay? The interval between two emissions is the same as the same interval between two receptions. Okay, so I can call this delta T emission. And I can call this one delta T reception. Okay? Are we together? Then we can go back to our expression for gravitational time dilation. Remember, we said that the tau is the same as 1 minus 2k over c squared r to the power minus a half dt. That's what we said earlier under gravitational time dilation. Okay? So if I now I can decide to write my delta tau emission, okay, to be the same as 1 minus 2k over c squared r. So this r will be r emission, okay, to the power minus a half delta t dot. And I can equally write the same expression for reception. 1 minus 2k c squared r to the power minus a half delta t dot. Any questions so far? So far, so good. So far, so good. Okay. So what if I divide the two? What if I divide the two? I'm going to end up with 1 minus 2k on c squared r e divided by 1 minus 2k on c squared r, all of that to the power, is it half or minus half? To the power is there a minus here? There's no minus there. There's no minus here. There's no minus. The minus appears only for length contraction. Okay, for dilation there's no minus. Okay. Are we together? Are we together? So now let's consider the emission of either a peak or a crest. Okay, the emission of either a peak or a crest as one event. Okay, the emission of either a peak or a crest as one event. And then let's consider n to be the number of peaks emitted in a proper time interval, the tau e. N is the number of peaks emitted in, okay, so if we are considering a crest, or maybe we can consider a trough, any of them, as an event, okay, and then n of them are emitted in this time interval. Okay, if n of them are emitted in that time interval, then what is our frequency? What's our frequency of emission? What's our frequency of emission? N over okay, that will be our frequency of emission. Our frequency of emission will be that. Okay, and we have agreed that the number of emissions will be the same as the number of receptions. There's no loss in signal. Okay, we don't have any attenuation anywhere. There's no loss in signal. Whatever is emitted is also received. Okay, so the frequency of reception will equally be defined as n over delta 2 r. Are we together? Are we together? Okay. So from there, I want to write the frequency of reception over the frequency of emission. It will be equal to n over delta 2r over n over delta 2e. So what would this be? It will be do we agree? Do we agree? Okay. If you don't agree, say you do. Don't go and grumble behind. If you don't agree, tell us that you don't agree so that we agree. Okay? Don't stay behind and grumble behind. Okay? And going by this, then this is the inverse of this, is that not? Comparing this and that. Okay? So what we are saying is that this is the same as 1 minus 2k over c squared re, okay, over 1 minus 2k. Let me write it the other way. It's the same as this to the power a half times this to the power minus a half. Okay? So we have that. So if we decide to expand that and assume that our c squared r e is far much greater than 2k. We assume that our denominator is far greater than the numerator. Okay? We assume that, then we can expand this out and retain only the linear terms. Okay? We neglect the higher terms. So we can expand this. So we expand this, we are going to end up with 1 minus k over c squared re plus that into 1 plus k over c squared rr plus other terms. Okay? So if we multiply that out, we're going to have 1 plus k over c squared rr. This is minus k over c squared re. Okay, so if we multiply this, we can neglect that term. Okay, we can neglect that term. So we have that. Okay, so this is going to give us 1 plus, we can factorize out the k over c squared. You have 1 over r minus 1 over re. Remember, this is that. Yeah, we are neglecting that term. We are neglecting that term. We are considering only this. Because of this, so we are leaving only the linear terms in R. Okay, so from there, if the 1 comes to the other side, we'll end up with VR. I'm calling it V, it's not V. What is that symbol? What is this symbol? What is the symbol? What is the Greek letter? Huh? What is this Greek letter? New. Is it new? New. This one is new. There's mu. Okay, which one is mu? What of this one? Okay. Into 1 minus RR minus 1 over that. So we have that. Okay? And I can write the left hand side as this, 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 which is the same as delta this over this. as the change in frequency over the emitted frequency. Okay. So the change in frequency over the emitted frequency, I can decide to call it Z. Can call it Z. Okay. So from this, you discover that if 1 over RE is less than 1 over RR, what happens? This will be positive. Is that not? This will be positive. If this term, if 1 over RE is less than 1 over RR, this will be positive. Because you have, this is greater than this. So once you minus it, you have a number greater than 0. So you discover that our delta 2 will be greater than 0. So in this case, is there an increase in frequency or a decrease in frequency? Is there an increase in frequency or a decrease in frequency? So there will be a okay. If this one is greater than 0, if this one is greater than 0, is the frequency of the receiver is more than the frequency of emission, is that not? If this is greater than 0, then this frequency of reception is greater than the frequency of emission. So what is happening to frequency? The frequency is increasing. So is there a red shift or a blue shift? It's a red shift. When frequency is increasing, okay, we'll start from there tomorrow. So go and think about it. We'll start from there tomorrow.